by taking the new fashion way, which is take the gene and turn it into E. coli and have E. coli express the protein before you isolate the protein that way. One of the first things you do is you do the characterized kinetics. You basically take the enzyme, add different amounts of substrate and reactant in there, and then see how it responds to the velocity. And then that gives you a preliminary indication of the type of enzyme it actually is. Okay, so we're going to get to the wire and sort of things. So last time we introduced chemical kinetics, and then this just quick review. In introducing chemical kinetics, we noticed that if we plot the initial velocity of reaction, that's the speed of the reaction before it even gets close to equilibrium, that initial velocity versus the substrate, the reactant concentration. I think I had it in A in when I showed it before. It's a linear response, like this. The more reactant, the faster that initial velocity. That kind of makes sense. And it makes sense because you have a higher concentration, so you're going to have a greater number of the specific atoms that have enough energy to get in the transition state to actually be able to get to the reaction. So this is chemical kinetics. But what I introduced right at the end of last time was the fact that if you do enzyme kinetics, we plot the substrate. And again, substrate is just an entomologist term for the reactant. That we get this hyperbolic response. And again, we're plotting against the initial velocity. At the beginning, it goes up, but then it begins to level off. At least at constant, this is at constant enzyme concentration. So we have to develop a mechanistic model that explains this hyperbolic response. And the model was derived by a woman named Maud Menton. She was a Canadian. She was doing a postdoc in the German laboratory of Lennon and Michaelis. And basically, she's the one that came up with this, building on some previous work of a guy named Paul Zane. Back in 1913, you guys remember 1913. All right, so the model came up with is, say we have our substrate with say we have our enzyme, and then we're mixing it with our substrate. That ends up forming, in a reversible form, an enzyme substrate complex. So that we basically have the enzyme substrate, and kind of forming a reversible complex. And every now and then we can give rate constants for this. So this is classically, that's K1, and this is K minus 1. Then the actual reaction occurs at the active site, and then we have another rate constant for that called Kcat, and which actually form an enzyme product complex, and then that degrades to enzyme plus product. Now, generally, it's considered that the dissociation of the product from the enzyme is not a rate-limiting process. So this equation is simplified to just E plus S 1 K minus 1 to the enzyme substrate complex, and then this is Kcat to the enzyme plus product. There are rare examples where it's thought that actually dissociation of the product from the enzyme is actually a rate-limiting step. But mostly this this model serves pretty well. And so we're going to basically work with this simplified model. So again, what we're trying to do is we're trying to explain this response where we increase the amount of substrate. We're increasing the amount of substrate, okay, and then we're measuring the amount of product. And then as we increase the amount of substrate, we flatten out and get this hyperbolic. So we basically need an equation that relates the velocity to the substrate concentration. And again, this is all a constant enzyme, so we want enzyme concentration there. So we're basically looking for an equation that has the initial velocity as a function of the substrate and the total enzyme. I'm going to put it as ET. So this is total enzyme. Yes. And I'm not going to put the brackets around here the whole time, or else I can freeze. All right, so let's have a look how that works. So the velocity, again, is the change in the amount of product over a unit time. So our initial velocity equals dp dt, right? And using this model, the most simple form, we can say, okay, that's going to be this rate constant times the concentration of this intermediate here, this complex. So this is going to equal K cat times ES. Now I'm trying to put the brackets back. So if we want to know what the initial velocity is in terms of substrate concentration and total enzyme, then we basically have to figure out what the relationship is between the enzyme substrate concentration of the enzyme substrate complex and the total enzyme and the substrate concentration. Okay. So in this derivatization, there are a couple of assumptions. The first is the equilibrium assumption. And then the equilibrium assumption suggests that formation of the enzyme substrate complex is at equilibrium. That is going, that this is going back and forth and it reaches equilibrium. So that we can define Ks as a dissociation constant for the enzyme substrate complex. And that's going to be the ratio of K minus 1 over K1, and which is going to equal the concentration of enzyme, free substrate over ES. So we're just kind of isolating this part of the equation, and we're looking at the ratio of, we're looking at how that equilibrium is formed between the free enzyme, the free substrate, and the enzyme substrate complex. that?
Are we going to integrate that again?
No.
Okay.
It's all out. All right. So now we're in our second assumption that we're going to solve is called the steady state assumption. And the steady state assumption is that the concentration of ES reaches a steady state. That is, if we look at here's concentration, here is time over here. And if we look at our accumulation of product, our accumulation of product goes here. This is all before we reach equilibrium. So this is all very early on. This is before we reach equilibrium. So here's product here. And so of course substrate is going to be here. And it's going to go down proportionally. That makes sense. Now notice I put these little lags in here, and that's because right at the very beginning, we put enzyme substrate, and we haven't reached equilibrium with ES, but eventually we do. And so if we look at the concentration of ES is going to go build up, and then it's going to flatten out over time. Because basically, as we build up ES here, then the rate moving forward begins to equal the rate moving backwards, and this becomes at a steady state. So the kinetics that we're talking about is all the kinetics in this region here. This is called steady state kinetics. And all this Michaelis-Menten equation and all that, it applies to the steady state kinetics. This really early period here, before we've actually reached steady state, this is called pre-steady state. And there's kind of a whole another field that looks at pre-steady state kinetics. And they have actually some pretty cool tools. They'll do what's known as stop flow analysis, where they have these machines that basically will take a tube, a reservoir connected to a reservoir of enzyme connected to a tube, and a reservoir of substrate connected to a tube, and then pump them through, and then they mix in a Y, and they're moving at a pretty fast rate. So it's a pretty narrow tube. The stuff is mixing comes to a Y, and it mixes together, and then you can basically then it moves down this tube after there's mixing, and if these are flowing at a high rate, you can basically study the processes before they reach at steady state by studying what goes on early after they've met that Y and are going on. So especially if you follow your enzyme substrate spectrophotometrically, you can just kind of have some spectrophotometric analysis going on right at that initial analysis, and you can get some all sorts of things. It's kind of cool stuff, but we're not going to get into it. We're basically focusing on steady state. Okay, so what the steady state kinetics means is that during the steady state, the rate of disappearance of ES equals the rate of formation of ES. So let's first of all, the rate of the formation of ES is going to be this K1 times E plus S. So the rate of formation equals K1 E times S. So the only way ES is made is from So combining E plus S and controlled by that rate constant. But then our rate of disappearance of ES is going to be both when it goes back to form free enzyme and substrate, as well as when it goes forward to form product. So the rate of disappearance of ES is going to equal, let's first do this, is going to equal K cat times ES. This moving forward that way, but also the breakdown of the ES complex back to free E and S. And so that's going to be K1 minus ES. K minus 1 ES. And if we're assuming the steady state, that this enzyme substrate complex remains steady here, then we can set this equal to that. So we basically have that K cat ES plus K1, K minus 1 ES equals K1 ES. All right. Now we can do some little simplification here. We can pull this ES out here, and so we can basically say K cat plus K minus 1 ES equals K1 and then we can pull this rate constant here out. We can divide through so that we can basically now get K cat plus K minus 1 over K1 times ES equals ES. All right. Now this term here has a special name. This is known as the Michaelis constant. Or more commonly known as Km. Now, there's a couple things, so let's think about, okay, what is that? So that's K cat here plus K minus 1 here divided by K1. So that's the ratio of the rate constants for the disappearance of ES divided by the ratio of the rate constants for the formation of ES. Okay, now there's one other thing I want to point out about this, is that in many enzymes, most enzymes, it's generally considered that the K cat is much less than K minus 1. That is, when the enzyme binds the substrate, it's binding the substrate and it's releasing, binding the substrate and releasing, binding the substrate and releasing. Only every now and then does it actually bind the substrate and convert it to product. Okay? So that this is much slower than actually the return to the opening up. So another way of saying that is in the special condition, when K cat, and it doesn't happen all the time, but I'd say most of the time, when K cat is much less than K minus 1, we're saying this is really insignificant, then Km more or less equals K minus 1 over K1. Let's go back over here. Oh, let's see what K minus 1 over K1. That's the dissociation constant for the enzyme substrate complex, which equals Kn. So what's that saying is that in most enzyme situations, the Km that you measure approximates the dissociation constant for the enzyme substrate complex. Our units end up being in molarity, and as well, I'll get to what that really means is that the Km is basically the concentration of substrate at which half the enzyme is bound to substrate and half of it is free. So Km approximates the substrate concentration when half enzyme is free and half is bound to substrate. So what does that mean practically? That means you measure this Km value, and if you come up with a Km value that ends up in the micromolar range, you say, that enzyme binds the substrate pretty well. It has pretty good affinity for the substrate. If it's down in the nanomolar range, it has really good affinity. But if it's in the millimolar range, it's not really, there's not that affinity, so that good affinity. So by measuring the Km, it kind of gives you an idea about how well the substrate actually binds the enzyme. All right, well, we kind of got off track a little bit by just introducing this whole Km thing. Remember, what we're really trying to do is we're trying to figure out our initial velocity in relationship to the total enzyme concentration and the substrate concentration. We figured out that our total velocity is K cat ES, but we got to basically replace this ES term here with something that has substrate and total enzyme concentration. So we haven't even gotten anything. In all of this, we don't have anything that has total enzyme concentration. So we have to kind of introduce that. Basically, where we left things was that, I guess we'll kind of summarize this, simplify this a little bit, is we can say that Km ES equals ES. All right, we're going to go back to that. But first of all, we have to bring in the whole concept of total enzyme. So the total enzyme equals ET, and that's going to be the free enzyme, E, plus the enzyme that's plus the enzyme that's bound substrate. So the total enzyme is going to be this enzyme plus that enzyme. That's pretty straightforward. Now what I'm going to do is I'm going to rearrange this and then also say basically our free enzyme equals our total enzyme minus our enzyme substrate. Okay, that's pretty straightforward, yeah? Okay, now we're going to come through there. Where do we leave ourselves here? And we're going to get rid of this free enzyme here by that substitution. So we're going to come in and we're going to now say our Km times S equals now our ET minus ES times F. I've basically taken this equation here and substituted for that free enzyme. Yes, thank you. Now we can multiply this through, basically, and now have ET times S minus DS times S. Now, so what you see, what we're doing now is actually we're isolating out. We're going to isolate our enzyme S and our ES and solve for that. So we can go back way over here, and we can substitute back in here at the very beginning. All right. So let's go ahead and pull this ES over. So now we have Km ES plus ds S equals dt S. We can pull this ES out here. Then finally solve for our ES equals dt S over Km plus S. Oh, all of that algebra. All right. Now we can finally get here. We go back over here. We have our initial velocity is a function of k cat times ds. We can do that substitution. Our initial velocity is now going to equal k cat times all of that. What was that? That was ET S over Km plus S. now we've got it. Now we have basically solved for the velocity of the reaction as a function of substrate concentration and total enzyme. And then we have some rate constants, our K-cat in here, and we have this collection of rate constants, which are the Michaelis constants. So this is the Michaelis-Menten equation. All right, now a little bit of caution. This is the most simple of the reactions, where you have one substrate giving you one product, right? And there are enzymes like that. Triphosphate isomerase takes a glycolytic enzyme, takes glyceraldehyde 3-phosphate versus dihydroxyphosphate. I guess isomerizes the molecule, and that would be a nice example of one of those kind of reactions. But most reactions end up having two substrates. Hexokinase takes glucose plus ADP, and then hexophosphate plus ADP. And you can basically go through the same, algebraic conniptions with those more, you just now have to add more terms into this equation, and you can basically go through the same thing, and you get more complex models, but they basically kind of follow a similar kind of pattern. So this is taking the most simple situation and trying to give you an example. And now what we have to do is we have to think about the meaning of some of these things a little bit. Everybody have this stuff down?
I have a question.
Yeah.
So I know you wrote it down on the board, but it's not clicking to me. Can you explain steady state? Like, what are we assuming there?
Yeah, so what we're assuming is that this is all our initial velocity, okay, when we're starting to accumulate. But we're recognizing that at the sort of very, very initial concentration, when we very, very first put our enzyme substrate complex, that this equilibrium has to get established. But once that equilibrium gets established, and then K-cat begins to work on this, you go through a period, still this is in the initial velocity, where the ES, the concentration of ES is at a steady state. That is basically the rate of its formation equals the rate of its dissolution. And it's assumption, it's an assumption. But it seems by having that assumption, it seems to work well, suggesting that it's a valid assumption. All right. So now if we plot our initial velocity versus our substrate concentration at a constant ET. So we're going back over here. Oh, I made myself walk back and forth. We're going back here. We're basically holding this constant, and then just changing the S's. Now notice as we increase the S's, because the S is both the numerator and the denominator, this will end up having the form of a hyperbola. Okay? So that basically what we're going to see, which is what we tend to see in enzyme catalyzed reactions, is this hyperbolic response. All right. The other thing that I want to point out here is this term K-cat ET. And K-cat ET is also known as V max. And basically, what happens is as you increase as you increase substrate concentration here, you drive drive this reaction to the right. You increase this up, you drive this reaction to the right, and theoretically, you could have your substrate concentration so high that you basically shifted this infinitely all the way here. When you shift it infinitely all the way here, all our enzyme is bound all our total enzyme is all bound in the enzyme substrate complex. Once all our enzyme is bound in the enzyme substrate complex, you've reached the maximal velocity, okay? Because now the reaction rate is going to be K cat times your ES, and your ES is maxed out because all your enzyme is bound to substrate, okay? And so that ends up becoming the asymptote that the hyperbola starts reaching, is V max, which again is KT times K cat. Now we can go through some more algebra, and I'm not going to go through some more algebra, but I'm just going to point out that, to demonstrate this, is that if this is 1/2 Vmax, our substrate concentration ends up equaling Km. Km equals 1, the substrate concentration if you want a little brain twister thing, show that algebraically. Basically, substitute in V max divided by 2 for V0, and then go through and solve for Km as a function of F. All right. Yep. Equals 1, or actually I can see V max over 2. Does that make sense? So this is V max, this is V max over 2, or 1/2 V max. Okay, so these are some classic interpretations of these graphs. Is that the asymptote that this approaches is going to be your V max, and then your the Km is going to equal the substrate concentration of 1/2 V max. Now the other thing I want to point out here is that all of that is at constant. We're holding a total enzyme constant. Now what we want to do is, what if we actually hold our S constant, okay, and increase the enzyme concentration? Well, the velocity is directly related to the total enzyme, right? So the more total enzyme, the higher the velocity you're going to have. So if we plot initial velocity versus the concentration of total enzyme, it just goes up linearly. This is at constant n. Now the functional interpretation of that is that you can use initial velocity as a surrogate measure of enzyme concentration. that comes in handy is, back when we were talking about protein purification, and we're saying, I mentioned that you could use an enzyme assay to, assay to measure the concentration of a protein coming off like this. So if you're doing the purification and you collect a bunch of fractions and you want to know, okay, where is your enzyme and which fractions have the most enzyme on there, you just take an aliquot, constant volume of each fraction, and you incubate it with the substrate of the reaction that your enzyme catalyzes, and you look for the presence of the product. And those fractions that generate the most product in a given amount of time are the ones that are going to have the most enzyme in them. So you basically just use enzyme activity, the ability to do the catalysis. Catalysis is a surrogate measure for the concentration of the enzyme. You really don't know how much enzyme, but you know is in there necessarily, but you do know that a fraction that generates more product has more enzyme than a fraction that generates less product. And so you can use that. Here's the other place where that's used is in like liver enzyme tests. So people who suffer from liver disease, one of the things that happens is there are certain enzymes within liver cells that that normally are isolated to living cells. However, to liver cells. However, if there's liver damage, the liver cells break open, and those enzymes are released into the bloodstream. So one of the tests for liver damage is to take some of your blood and have it look for the ability to catalyze these reactions that normally only take place in the liver. These are known as the liver enzymes. They tend to be enzymes involved in myosin metabolism, alanine aminotransferase, these sorts of things. And so I don't know if you guys ever have had a liver panel or a liver assay. What they do is they basically use the catalytic activity in the blood as a surrogate measure of whether or not these enzymes exist in the blood. And if they exist in the blood, it suggests that there's been some damage to the liver and those enzymes have been released from the liver into the blood. Okay. Oh, this stuff is all right. Okay, so a little bit more K-cat. K-cat is also known as the turnover number. It has the units of time to the negative 1. So seconds to the negative 1. And it basically tells you an individual enzyme molecule will generate how much product in 1 second. Can develop the turnover number. So let's finish up with K-cat over K. There's another ratio which is called K-cat over K. This is known as the catalytic efficiency. It's used all the time. I'm not that big of a fan of it, but it's used all the time. I think K-cat and Km kind of tells you some things differently. The argument for using it is that if we go back to our Michaelis enzyme, our Michaelis Menten equation, B0 equals K-cat times our total enzyme times our substrate over Km plus our substrate. At very low S, this term here much less than Km, then B0 equals K cat over Km times ET S. So it basically is like if you have hardly any substrate in there and a substrate binds an enzyme, sort of what's the combination of both the binding affinity as well as its ability once bound to turn over to product. That ends up being basically both incorporates both aspects into it. So it's basically, this ends up becoming a second order rate constant. When S is much less than Km. Okay, where is this used? This is used in like site-directed mutagenesis studies. The site-directed mutagenesis is when you might take an enzyme and you might modify it, and you're trying to examine what the role of particular amino acids are in the catalytic function of the enzyme. And so in order to do that, you might actually go in and start modifying, genetically engineering the protein. So instead of having a histidine at the active site, maybe it has a carboxyl group at the active site, or histidine at the active site, maybe it has an alanine at the active site. And then once you have made this mutant protein, you do the kinetic characterization, calculate Km, calculate Kcat, and figure out Kcat over Km, and use that as a relative measure. Okay, what's the catalytic efficiency of this mutant relative to the wild type or relative to some other mutant? Okay, a lot of algebra here, a lot of math. There's there'll be some problems.